Chances are you're either studying for a test or studying for an interview, and you need to know about pressure vessels. Now, axial stress and hoop stress are the two kinds of stresses you need to know when it comes to pressure vessels. I'm going to go over a short little explanation about how you can intuitively understand this topic, and afterwards, if you're still interested, I'll go over the derivation on how you get their formulas for the two stresses. So if we look at a pressure vessel, all it is it's some sort of cylinder. Now, it could also be a sphere, but we're just going to be talking about cylinders for now. And the biggest question that lots of people ask is, well, why is hoop stress twice as large as axial stress? Now, just to clarify, axial stress is going to be stretching out the pressure cylinder lengthwise. Okay, so it's going to be going like this way, right? So axial stress is pulling it apart lengthwise, or you're elongating it. You're making its length larger. Hoop stress is going to be where you're going to be changing its diameter. Okay, so in this scenario, that would be going like this. This would be hoop stress. Now, if we look at these two things, we need to ask ourselves, what is easier to do? Okay, so let's look at this. This is going to be our axial stress because it's elongating it, stretching it out. And this is going to be our hoop stress. Okay, and this is going to be stretching out its diameter. Well, we need to think. If we're going to be stretching out its length, that's going to be harder because there's more length. There's more material lengthwise. So all of that material is going to be resisting it much better than the hoop stress. Hoop stress is going to be pulling more against its diameter, and there's not as much material that way. So it's going to be easier to stretch it out through its diameter. Okay, and that is why your axial stress is equal to 2 times your hoop stress. Okay, and that's just a really simple explanation of why that is. Now, if you need to know a more technical way to show this, let's do that. We'll start by talking about axial stress because it's a little harder to derive, in my opinion. It might be easier for some of you. Now, again, axial stress is going to be stretching it lengthwise, okay? So we need to think, how does the pressure inside of this pressure vessel stretch out its length? So the way that's going to happen is if we have pressure going around the rim like this, right? And so this pressure is applied everywhere because that's the way pressure works. And it's also going to be inside of here too, right? It's acting over that area where this is our radius. Okay, and this is going to be our pressure. Now, opposing that pressure is going to be our axial stress. So let's draw that. And the axial stress is going to be happening in the material where we have an actual material, right? We won't draw it in the middle because there's no material in the middle. That's all your liquid, your fluid, to be more general. So this is going to be our axial stress. Now we know that the forces due to this pressure and due to this axial stress are going to have to equal each other. How do we know that? Well, if they didn't, our pressure vessel would blow up. And we don't want that because, well, I don't think I need to explain that. So we're going to look at the sum of the forces in the x direction. And so we will call right positive. Right? We know that sum of forces is equal to 0. Again, because we want these to equal each other because we don't want our pressure vessel to be blowing up. Let's start in the positive direction. So if we look at the axial stress, we see that that is heading in our positive direction. Now, how do we write a stress in terms of a force? Well, we know, I'll write it over here, we know that our pressure is equal to force divided by area. So all we have to do is say pressure times area is equal to force. Okay, let's keep that in mind. So let's look at this axial stress. So we say axial stress times the force that So we say axial stress times the area that it's acting over minus pressure times the force that it is acting over. Okay, so we'll call this AP. Okay, now let's look into these things a little more. So what's the area that the axial is acting over? Well, that's going to be the rim, right? Because it's going to be wherever the material is. Let's draw that in. It's going to be this. This is going to be the area that the axial stress is acting over. So how do we write that? Well, it's pretty simple. We just subtract the two circles that make it up, right? So if we call this right here our thickness, T, well, then we can say our area is equal to pi times r plus t squared minus pi times r squared, right? That's the outer circle minus the inner circle. Okay, this doesn't just turn into r squared plus t squared. This becomes r squared plus 2rt plus t squared. Okay, now we're going to distribute that pi, and we see that we get pi r squared plus pi 2rt plus pi t squared minus pi r squared. We see that we get this guy's going to cancel and this guy's going to cancel. Right, now let's look at this guy right here, pi t squared. Now we can do something special here because our thickness for our pressure vessel is going to be much, much smaller than our radius. Now what does this mean? Well, because it's on its own and because it's being multiplied by itself, that's a super small number that's being multiplied by another super small number, this is just going to become negligible, okay? So we're going to ignore it. We're going to treat it as 0 just because we have the property where our thickness is much, much smaller than our radius. So we get that the area that our axial stress acts over is equal to 2 pi RT. Okay, now let's look at the area that our pressure acts over. So we see that it's just going to be that inner circle we were talking about. So that's really, really nice. Okay, we can just say that area of pressure is equal to pi r squared. Super simple. So now let's go back up to this equation and we can plug things in. We can say that our axial stress times the area it acts over, which is 2 pi RT minus our pressure times the area that it acts over, which is pi r squared, is equal to 0. Now, with a little bit of magic, let's take a look at what happens. We get 2 times our axial stress times pi RT is equal to P times pi r squared. We want to isolate that axial stress, so we get axial stress is equal to P over PR over 2T. Okay, and that is how we derive axial stress. Now, hoop stress is going to be what stretches our diameter out. So we need to think, how do we stretch our diameter out? And it's when our pressure is applied in a certain way. And it's when it's going to be applied looking like this. So we have our pressure all applied like this. And I'll go into this cross section a bit more so you can have a better idea. But this is going to be our pressure, right? And then opposing that, we're going to have our hoop stress. Okay, and we can see here that what this would do is this would stretch out our diameter. Okay, this is our hoop stress. Now we're going to do very similar thing that we did last time. We're going to do force equilibrium, but in order to do that, we need to look at our areas and do all that fun stuff. So over here, we have a little nicer of a picture. And so let's define some traits. So this right here, well, if we called the whole thing length like we did right here, then a small piece of that, let's call it DL, or a small chunk of the length, Okay, now from the center of this to there, that's our radius, right? Nothing new there. And that's it. That's all we need, other than our thickness, which we defined earlier. Thickness T. Okay, so knowing this, let's see how we can get our hoop stress. So we're going to start in the exact same way that we did before, and we take the sum of the forces. We'll call the right positive. We know this is equal to 0 for the same reason as before. We do not want exploding pressure vessels. So we say, well, this time pressure is to the right, so we want the pressure times the area that the pressure acts on minus the hoop stress times the area that the hoop stress acts on. Okay, now let's take a look and define the area that the pressure acts on and then the area that the hoop stress acts on. So the area that the pressure acts on is going to be this rectangular area here, like that. And we can see that that's made up of two radiuses, or diameter. So, and then that's 2r, and then times that dl, right? Because it's just a rectangular area. So very simple. So dl times this length here, which is 2 times the radius. Now, let's go over our hoop area. A hoop area is a little bit more difficult, but not that much. The thing that you have to keep in mind is that there's two pieces here. So let's look at our hoop area. Our hoop area is going to be this, right? Because that's the material. So the hoop stress is going to be on the material. So we see that that's going to be, well, that rectangular area right there, that's going to be T times dl. And then we also have it down here. So that's also going to be T times dl. If we add those two up, we get 2T dl. Now, this is going to be really easy. Same thing we did last time. Let's do a little bit of magic. Say that pressure times the area over pressure is equal to the hoop stress times the area that the hoop stress acts over. Now we plug things in, and we are going to isolate hoop stress. So pressure times 2r dl equals hoop stress times 2 thickness dl. Isolate that hoop stress, we get that hoop stress is equal to pressure times the radius divided by thickness. And that is how we get a formula for hoop stress. So in the end, we see that axial stress is half as large as the hoop stress. So that's an important thing to know if you're going into a test or an interview. Just try to remember that. Good luck.